Hello everyone. In this video we will be taking a look at uniform circular motion. That is, we have an object moving around a circle with a constant speed. Moving at a constant speed might make your instinct say there's no acceleration, but since the direction of motion is changing, that means our velocity vector is changing direction as time passes. Something like that can only happen if there is an acceleration. It turns out that there's a nice formula for what that acceleration has to be for our circular motion to happen. We call this type of acceleration centripetal acceleration, and it is given by the velocity squared divided by the radius of that circular motion. This special type of acceleration always points radially inwards to the center of the circle. We can apply centripetal acceleration to Newton's second law of motion and make a net force equation. Since the centripetal acceleration is always radially inwards, the component direction of forces that we add up must all be radial, that is, going directly into or out of the circle. When making these types of net force equations, we conventionally choose that any forces going into the circle as positive, meanwhile going out radially from the circle is negative. For our first example, a 1 kilogram ball on a string, which is 40 centimeters long, is being swung in a horizontal circle. If the ball is being swung with a speed of 3 meters per second, what is the tension in the string? This question is asking about the tension, which is the force along the string. We know the ball is moving in a circle, so the acceleration must be v squared over r, as well as that acceleration must be radially inwards to the center of the circle. Since this problem involves forces and acceleration, we can draw ourselves a free body diagram. In this case, the ball is being swung in a horizontal circle, like if you were swinging that ball up above your head. So we might want to draw things from an overhead view to see the circle. So maybe here could be the center of the circle, and the ball is going in a circle around that center. For this problem, we're free to draw the ball at any point along this circular path, and the direction doesn't really matter, so I'll just say it's going counterclockwise here. So at this moment, v is tangentially in this direction. And I know there's a string connecting it from where I'm swinging it here in the center. Since we're drawing a force diagram, we would now want to draw any forces that were acting on this ball. In this case, we have a string, so we know there might be tension along that string. Recall that tension always goes along the direction of a string or rope, which, since the rope is radially inwards from where the ball is connected to it, tension must also be radially inwards. Technically, there is also gravity here, which always pulls towards the Earth. The way we've drawn our horizontal circle here, like we're looking at it down from above, then the force of gravity would be directed into the screen. That being the case, that makes gravity not a radial force. It is not going into or out of the circle. It is going in a direction that is completely perpendicular to the plane of the circle. We will be neglecting it. And that will be the case for all horizontal circular motions in this course. So in the end, this means that for this problem, tension is our only radial force. So when we go to make our net force equation, tension being the only radial force means the left side just becomes tension. So we see that tension has to equal whatever the mass is, which is 1 kilogram, multiplied by the centripetal acceleration, which we know has to be v squared over r. In this case, our velocity is 3 meters per second. So square that and divide by the radius of our circle. Now do always pay close attention to all your units. The string in this case is 40 centimeters long, so the length from our center is 40 centimeters. So we have to take that 40 centimeters and turn it into meters to plug it into our radius. In this case, if we convert that, that is 0.4 meters. So we'll plug in 0.4 meters. Doing this calculation will give us a tension equal to 22.5 newtons. Now let's take a look at a vertical circle problem. A person with a mass of 70 kilograms has gotten on a Ferris wheel that has a radius of 30 meters. The ride takes 2 minutes to complete a full rotation. Find the apparent weight of the person at A, the top of the ride, and B, at the bottom of the ride. Recall that the apparent weight should be associated with the normal force. So we are looking for a force that is acting on an object which is going in a circle. We might want to start by once again drawing our free body diagram, first for the case of being at the top of the ride. So here's the circle representing our Ferris wheel. Here we are riding the cart at the very top of the ride. Now what forces should be acting on us? In this scenario, we now have a vertical circle, which means gravity is something that we might want to consider as something that could be radially inwards or outwards. In this case, the force of gravity always goes vertically downwards, so at the top of our circle, it goes into the circle. Also, since this person is sitting or standing in that cart of the Ferris wheel, they're being held up by a floor or a chair, so they're experiencing a normal force, which would be pointing straight upwards. And again, since we are at the top of the ride, that upward force ends up going out of the circle. In this scenario, we've now drawn all the relevant forces, so we can go and make our net radial force equation, which, since we are going in a circle, must always equal mass times that special centripetal acceleration. Here's where things become slightly different than how we used to handle vertical forces. Normally, if we're doing a net force equation in the y direction, we call up as positive and down as negative. However, since this is a radial force equation, the convention is typically to call inwards forces as positive and out as negative. Since gravity is going into the circle, that means the mg should get a positive, while the normal force should get the negative. The reason we choose this convention is because when we go to plug in the centripetal acceleration as v squared over r, since that centripetal acceleration is into the circle and v squared over r is always a positive value, this will help keep all of our signs consistent. So let's think about if we have everything we need to plug into this equation to solve for our one unknown, which is the normal force. We have the mass and we have gravity. We're looking for the normal force. We have the radius of this Ferris wheel, which is r equals 30 meters. However, we don't have the velocity we are moving around this circle at. We do know that it takes 2 minutes to complete a full rotation, so maybe we could use that. When it comes to circular motion, we have some other equations we might want to keep in mind, such as the velocity that we move around the circle can be found by doing 2 pi r, which is the circumference going around that whole circle, divided by this capital T, which is the period it takes to go around that circle. So if you think about this equation, it makes sense. 2 pi r is the distance you travel around the circle, divide by the time it takes to do so, and that gives you a speed of some sort. Do pay attention that the period in this case was given to us as 2 minutes, which means we would have to convert that to seconds. Since there are 60 seconds in a minute, 2 times 60 will give us 120 seconds. So let's plug everything in to get the velocity. 2 pi times the radius of 30 meters divided by the time of 120 seconds ends up simplifying to pi over 2. So if we start plugging into our net force equation, 70 kilograms for our mass times gravity of 9.8 since we're on Earth minus the normal force which we are looking for equals the 70 kilograms multiplied by v squared, which is pi over 2 meters per second squared, divided by the radius of 30 meters. 70 times 9.8 will give us 686 newtons minus the normal force has to equal 5.757 newtons about. Moving things around, we get the normal force should equal 686 minus that 5.757, which will give us about 680.243 newtons. So this normal force is the apparent weight they are looking for. Now let's see what changes when we are at the bottom of the ride. We'll have to redraw our diagram, so here we are at the bottom. This time, gravity going vertically downwards would be away or out of the circle. Meanwhile, our normal force, which is keeping us held up, would be into the circle. So when we go to make our net radial equation now, The normal force is positive going into the circle, so N minus the gravity going outwards will be equal to the mv squared over r. So the normal force will equal mass times gravity plus mv squared over r, and we have everything we need to plug into that. So N equals the 70 kilograms times 9.8 plus 70 times the v squared over r. In this case, at the bottom of the circle, we find that the normal force, or apparent weight, will be about 691.757 newtons. So we can see how our apparent weight might change depending on whether we are at the top or bottom of this Ferris wheel.